Hi guys, Mrs. Rossi here. Today we're going to be talking about the trends and periodic trends that go across the periodic table, also called the periodicity of elements. You have your note sheet from class. Hopefully you've already reviewed some of the periodic table stuff you should already know because we're going to be referencing all of that stuff as we go throughout today's presentation. So some of the stuff that we want to review about the periodic table is what is special about the noble gases. You should know the noble gases are group 18 on the periodic table, all the way over on that right-hand side. So here are your noble gases right here. And they all have full valence shells. So they have full sets of valence electrons. For helium, this means it only has 2 valence electrons, but for the rest of them, they all have 8 valence electrons. After that, what is the middle block of elements called? So this middle block right here, these are your transition metals. Remember, your lanthanides and actinides are also part of that. Those 2 rows that I just pointed out, the lanthanides and actinides, we know they actually fit in right here and right here on the periodic table. Elements in the same group, they have a lot of things in common. Remember that groups are also called families, so they share a lot of similar physical and chemical properties. They also have the same number of valence electrons. Why do elements in the same groups have same physical and chemical properties? It comes from their electron configuration. So since their ending electron configurations are all similar and they all have the same number of valence electrons, they all behave in similar ways. And then last one, what does periodic mean? Periodic means happening at regular intervals. So the periodic table gets its name because these patterns and trends of physical and chemical properties happen periodically, so trending as we go period by period down the periodic table. So we're going to get a closer look at a few periodic trends today and make sure you're following along with your note sheet as well. The first periodic trend we're going to talk about is the atomic radius. The atomic radius gives you pretty much the relative size of an atom. It's a measure of how wide an atom is at its widest part. Now, it's not like you can go in and just measure the distance from the nucleus of an atom out. It's not easy to do. We know atoms are really small. We know that they're constantly in motion, and we know those electrons in the electron cloud are also constantly in motion, and we can't actually predict where they are. So, to figure out the atomic radius, or the relative size of an atom, scientists take atoms that are bonded together. Think Bringelhoff, all of our diatomic atoms that we talked about. Since they know how far the nuclei are apart in a bonded atom, they can do 1/2 the distance between 2 atoms in a diatomic molecule. That half gives you the radius of the atom, so the distance from the center of the nucleus out to the furthest part that you can find the electrons. And this gives us the relative size of an atom. On the periodic table, there are trends with the atomic size. So as you move from left to right, so starting at the alkali metals and going over towards the noble gases, so left to right across the period, and the principal energy level stays the same, the atomic size generally decreases. So from left to right, atomic size generally decreases. This is because you're not increasing the energy level. So you're at the same energy level as you go across that period, and that nuclear charges, positive and negative poles, are getting pulled closer and closer into the nucleus. So that positive charge of the nucleus is pulling in those electrons tighter and tighter. They can't spread any further apart because they're not in a higher energy level. So then it should make sense, our group trend, as you move down a group, atomic size generally increases. So atomic size generally increases as you move down a group. This is because you're adding more and more energy levels. So you're getting further and further away from the nucleus. The radius is getting bigger and bigger as you're adding energy level after energy level. So here's a trend as you go across, so left to right across the group. You're staying across the period, and you're staying in the same energy level. You have decreasing atomic radii. As you go down a group, you're adding energy levels, so you have increasing atomic radii. They're getting bigger and bigger. So let's try to actually figure out what's going on with these if we had to put these in order. So we want to rank chlorine, fluorine, iodine, and bromine in order of increasing atomic radius. So we're starting with the smallest, going to the biggest. find these on your periodic table. So we want to find chlorine right here, fluorine right here, iodine right here, and bromine. It might be a good idea, especially if you're using one of the laminated periodic tables, to make little marks for yourself so you know what you're actually looking at. So we want to put these guys in order of increasing atomic radius. Well, if you remember the trend, as you go down a group and all of these elements are in the same group, atomic size generally increases. So to put these guys in order, fluorine would come first, chlorine would come second, bromine, and then iodine would be our largest. We're going to do the same thing, but this time we're going to put sodium, aluminum, silicon, and magnesium in increasing size order. So again, if you're on your periodic table, you kind of want to mark off what elements we're looking at. Notice they're all in the same period, so they're all in the same energy level. The smallest one this time, so because we're going in increasing order again, is going to be silicon. So silicon's your smallest, then aluminum, then magnesium, and sodium would be your largest. This is because as you go across a period, atomic radius decreases. Our next trend that we're going to talk about is ionization energy. Ionization energy is the energy required to overcome the attraction of the nuclear charge and remove an electron from the gaseous state of an atom. That sounds really complicated. What ionization energy really is the energy you need to pull off an electron from the valence shell of an atom. So it's the energy you need to pull off an electron from the valence shell of the atom. There are multiple ionization energies. There's a first to pull off the first electron, second to pull off the second electron, third to pull off the third electron, and so on. We are going to focus on the first ionization energy only. So here's an example of the different ionization energies that there are depending on how many electrons you're pulling off or which electron you're pulling off. We're going to stay focused up here at first ionization energy to look at trends. So the first ionization energy generally increases, meaning you need more energy to pull electrons off as you move from left to right across a period. This should make sense because as you are going from left to right across the period, you're adding more and more valence shell electrons. The valence shell electrons are increasing, so the electrons in the valence shell have more buddies as you're going across, and it's harder and harder to pull them away from each other. This trend is not true for all transition elements, but it does work for those main group elements on the rest of the table. So we're going to go with the first ionization energy increases as you move from left to right across the period. Moving on to groups, the first ionization energy generally decreases as you move down a group. And it's actually for a similar reason that the atomic radius increases as you go down a group. So as you go down a group, those energy levels are increasing. Those electrons are getting further and further away from the nucleus, further and further away from that positive charge. So it becomes easier to remove one of those outer shell electrons because it's not as close and it's not experiencing as much of a charge as those ones that are closer into the nucleus in those first few energy levels. So here is the general trend of first ionization energy on the periodic table. You have increasing as you go across the period, decreasing as you go down a period or down a group. All right, so let's take a look at certain elements to try to put them in order of increasing ionization energy. We're going to do the same thing that we did for atomic radius, but this time we're going to be looking at oxygen, selenium, tellurium, and sulfur. So remember, we want to go in increasing ionization energy order. Ionization energy, as you go down in the group, decreases. So the smallest ionization energy would be with tellurium, and then selenium, and then sulfur, and oxygen would have our highest ionization energy amount. Why don't you try to rank the next ones? So you're going to be looking at lithium, carbon, nitrogen, and fluorine. Take a minute, pause the video if you need to rank those in order of increasing ionization energy. Our next periodic trend is ionic size. This might sound similar to the atomic radius because it's talking about the general size of an atom, which is true, it does follow that trend, but now we're talking about the size of ions compared to the neutral element. So this is when some of those electrons have been ripped off or given up or taken in. So we're talking about a neutral element, same number of protons and electrons, to its ion, different number of electrons. So cations are always smaller than the neutral elements from which they form. Hopefully this should make sense. Your cation, you're giving up electrons, becoming positive, you're going down to a smaller energy level. Negative ions are always larger from the neutral atom, larger than the neutral atoms from which they form. So this should also make sense. You're completing that energy level. So you're adding another electron to the electron cloud, and it's moving around all crazy, and they're trying to spread out, making the atom a little bit bigger. So cations are always smaller. Negative ions, your anions, are always larger than the neutral atoms from which they come. There is a general trend, no matter if it is a cation or if it is an anion, with the size of the ions as you go across a period and down a group on the periodic table. Going from left to right across a row, there is a gradual decrease in size of the positive ions, and then when they switch to negative ions, there's another general decrease in size. So depending on where you're looking on the periodic table, whether it's at the metals or the nonmetals, remember metals form cations, there is a slight decrease in size from left to right, and then when it switches over to your anions, there's another slight decrease in size of the ions as you go down. Down a group, this should also not be surprising because we're talking about larger and larger energy levels as you go down a group. The ionic size of all elements increase as you go down because you're adding more and more energy levels. So why don't we take a look at some of these ions and their neutral elements so we can compare. Here's lithium, normal lithium, same number of protons and electrons. Remember, there's 3 protons, 3 electrons in lithium. And here's when lithium gives up that 1 valence shell electron, becoming a lithium cation, much smaller. So cations are always smaller than what they came from. You can see that same pattern with sodium, beryllium, and magnesium. And now here's neutral fluorine over here. When fluorine, which has 7 valence electrons, fills its valence shell, so adding another electron, now we have our fluorine anion, which is much larger than the fluorine it came from. We see the same thing happening over here with the chlorine anion. Here's our general trend of cations and anions as we go down and across the periodic table. Cations, we know they decrease as you go from the left to right, and then anions, even though they're generally larger than the cations, still follow the decreasing trend. And then both cations and anions, doesn't matter, increase in size as you go down a group. So ionic size increases as you go down a group. Take a minute, look at these cations and anions, and circle which one is larger for each pair. Up next, and this is the last trend we're going to be talking about today, is electronegativity. The electronegativity of an element is the tendency for atoms of the element to attract electrons when they're chemically combined with atoms of another element. Also, sounds complicated, but it's really not. Electronegativity is how good an atom is at pulling electrons to itself. So, does it really want to complete its valence shell, or would it be easier for the atom to kind of give up its valence electron to get down to a full valence shell? The goal for electronegativity is to have a full valence shell, and atoms that are really good at pulling in are going to have a high electronegativity, and atoms that really aren't are going to have a low electronegativity. Here is a periodic table of electronegativities. So you can see over here, pretty low electronegativities with our alkali metals and alkaline earth metals. The transition metals in the center, they kind of have medium but still pretty low electronegativities. And then up over here, our nonmetals are a lot better at pulling electrons to themselves because they have almost full valence shells. Here's fluorine over here. That's the highest electronegativity you could have. It's on a 0 to 4 scale. So fluorine is the best element out there at pulling electrons to itself. You can think of it as being the strongest element out there. Notice that the noble gases over here do not have electronegativities listed. This is because they don't have electronegativities. They don't like to bond with other people. They already have full valence shells, so their electronegativity you can just think of as being 0. The trend with this, and you probably picked up on it from looking at that last slide, as you go from left to right across a period, electronegativity increases. It stops at the halogens, though. Don't include the noble gases in that. So the noble gases, even though they're all the way on the right-hand side, we know they don't have electronegativities. So it stops at the halogens. Down a group, electronegativity decreases. So as you go down a group, your electronegativity decreases because those energy levels are getting bigger and bigger out. There's shielding that takes place by those inner electrons, so they're not quite as strong or as good at grabbing electrons from other atoms. So the electronegativity of larger elements tends to be less. So here's our general trend of electronegativity again. We have increasing from left to right, and then it's decreasing going down, or you can also think of it as increasing going up. You can put either a decreasing arrow going down, if you'd rather write it out that way, or increasing arrow going up. Remember, fluorine is your most electronegative atom. Noble gases don't have electronegativities. Here's just another representation of the different elements and their electronegativities. You can see how fluorine sticks out. Hydrogen, we know, is one of those special elements and it's not actually a metal, so that's why it has a little bit of a higher electronegativity. Noble gases all the way down because they don't have an electronegativity. So why don't you give it a try one more time? We want to rank in order of increasing electronegativity. Notice the one that's up on here. We have fluorine, boron, oxygen, and lithium. So they're all in the same period. You should remember that as you go across, electronegativity is increasing. So lithium would be the least electronegative, and then boron, and then oxygen, and fluorine is the most. The next ones you have to try, barium, calcium, beryllium, and strontium. So take a minute, try to organize those from an increasing electronegativity. So that's from the least to the most electronegative. Think about electronegativity down a group as you do it. The next and last thing you have to do to go along with this presentation is figure out if these statements are true or false. You can either go back in this video presentation or go back into your note sheet to try to figure them out.